Okay, I wanted to go through this and talk about when we might use substitution and whether it might be a good approach and whether it's not a good approach. In something like this, you might let u be x, but then that doesn't change it because x was a change to u's and dx equals du. Nothing's going to cancel, so this one, substitution, is not a good choice. It doesn't get you anywhere. If you let u be x squared, though, the derivative is 2x. If you let u equal x squared, du equals 2x dx. If you solve for dx, you get a 2x underneath the du. So the dx becomes du over 2x, and the x's cancel, and so we just have sine of u with a half on it, but the x would cancel. So this is a good candidate for substitution. This one probably would think about letting u be ln x. And if you take the derivative, you get du equals 1 over x dx. So that x comes up and becomes times the du. So dx would become x du, and that x would cancel that x, and we just have sine of u. So substitution is a good choice. Now this one, if you let u be that, you get dx would become x du, and you would have this x hanging around. You'd have sine of u, but with an x du, the variables wouldn't match, and so this one is not a good choice for substitution. This one, if you let u equals x squared plus 2, du would turn out a 2x dx, so you're going to get a 2x under the du, and the x's would cancel. The 5 and 2 comes out, so this one will work with substitution, because you're going to only have 5 over 2 coming out and the square root of u. On this one, same thing inside, you're still going to get that 2x, du over 2x, cancels one of the x's, but not the other one. Now you may use substitution at some point in this, but it ain't going to be enough to finish this one, so you're going to need substitution and more, or maybe not even substitution at all. We don't know. On this one, if you let u be 5x to the 5th, you should see that du would be 25x to the 4th. That 25x to the 4th goes in the denominator, and the x to the 4th would cancel. So this one is a good choice, a good candidate for substitution. This one, if you let u be sine x, du would be cosine x dx. So the cosine would end up underneath. Canceling the cosine, you just have the integral of u dx. Or you could have let u be the cosine of x, and its derivative would be negative sine x dx, and the sine would go in the denominator, and you'd have u with a negative on this du. So this one will take u as either sine x or cosine x and will work. So this is a good candidate for substitution. And we've already talked about one like this. Letting u be the sine x doesn't help much because you get a cosine x in the denominator, like we would here. If you let u be cosine x, then you get a sine x in the denominator. It would cancel the sine x in the numerator, and you would have 1 over u. So using cosine x as the u substitution, this one works. And if you let u be cosine x on this one, the dx becomes du over negative sine x. And one of the signs cancel, and this cosine becomes a u, but the other sine x doesn't cancel, so we have a sine x over u du with a minus, but it's not going to work very well. So hopefully as I'm doing these, you're starting to see what to look at when you're trying to decide if you should use substitution. Now in this one, again we'll do the same substitution for that denominator, cosine. So the dx becomes du over minus sine x. The cosine x becomes a u, because that's what we let it be. This sine x cancels one of those, and we get sine squared. And you think, maybe this is not working, but it does, because sine squared of x, according to the Pythagorean theorem of trigonometry, sine squared plus cosine squared equals 1, sine squared of x is equal to 1 minus cosine squared of x. And we'd have u down here, du, and a minus. But cosine x is what we let u be, so we'd have 1 minus u squared over u with a minus 1 du. This is u to the minus 1. We can divide the u into both of these, and we get minus the antiderivative of 1 over u, and minus u squared divided by u is just u du. We can do the integral of that and the integral of that, two separate because they're added or subtracted, and we can get this one to work. So substitution did work on this one. So it worked when it was to the 1, not when it was squared. Does work when it's third, won't work when it's fourth, will when it's fifth, so on and so forth. So it makes a difference whether it's odd or even. This one, if you let u be x squared, of course you know that'll be du will be 2x, and we'll get the 2x in there du, and that x will cancel that one. The 7 over 2 will pull out, and we'll have e to the u, which we can do. But if it's x squared, and we get that, do that same substitution for the x squared, we get let's actually do this one. So this would be du over 2x. X squared is u. The x cancels 1, and we just have an x left. And so we'd have the integral of 7 over 2, which we can pull out, x e to the u du. Can't have an x. We could go back here and solve, and we'd take the square root, and so we could put the square root of u there, but that's still messy. Substitution has problems. This one, if you let u be the square root of x, which is x to the 1/2, its derivative is 1/2 x to the minus 1/2, which is 1/2 times 1 over x to the 1/2, which is 1 over 2 square root of x dx. So if I end up solving for dx, I'm going to multiply by 2 square root of x. So I'm going to get 2 square root of x du to replace dx with. So dx would become 2 square roots of x dx, du, and the square roots would cancel, and I get e to the u to integrate. So substitution works on this one. And what you should notice is that if you let u be square root, you end up with a square root in the denominator, which ends up in the numerator. So if you let u be a square root, it'll cancel square roots in the denominator. If you let u be the square root on this one, you get a 2 square root of x du, and the square root of x doesn't cancel, does it? We actually get that squared. And so we'd have the square root of x times the square root of x times u to the square root of x, but we let u be the square root of x, so we'd have u squared e to the u with a 2 integrated du, and that's messy. Substitution is causing us problems here, so not a good candidate. Might work eventually, you might have to use it somehow, but not working right away. This one, if you let u be e to the x, the derivative is e to the x. If you let u be x squared, the derivative is 2x in the denominator, but that'll cancel there, but then we'd have to figure out how to do this one. This is not a good candidate. It's not going well. Look at it closely if you need. And I put these two on there that I didn't do in class just for a particular reason here. What would you let u be? Well, you might let u be ln x. So du would be 1 over x dx. The x comes up. Is that going to cause problems? Well, this would become the integral of the 5 would pull out. We have x squared ln of u. No, we let ln of x be u, so we got u, and dx becomes x du, so we got x to the third. So can we solve for x in this? Well, if u equals ln x, x equals e to the u. To what power do we take e to get x? We take e to the u to get x. So we could replace the x's in here with e to the u, so we'd have 5 integral x to the u would be e to the u squared, so it'd be e to the 2u times ln, which is u, and it's not going so well. So probably not going to do substitution. And same, well, here you might let u be x to the third. Its derivative is 3x squared. And so we're going to get an x squared in the denominator when we replace dx. Du over 3x squared. The x squareds cancel, and we'd have ln u. But what is the antiderivative of ln u? We'd have a 5 and a 3 that would come out, and that is not obvious. The derivative of ln u is 1 over u, but the antiderivative of ln u is tricky. So substitution helps, but it doesn't get us to the answer. So we might have to do substitution and something else. So what? And that's coming.